deep neural networks to predict the future state of the weather, given the current state of the weather, and very successful at it. And then there's a whole bunch of very interesting applications that are enabled by these new techniques. Maybe the most, and they have a very big societal impact. For instance, the top one there is the generation of new molecules. So this is a system where basically you start with a bunch of you start with a pocket, which is the pocket of a protein, and you're trying to generate a particular molecule inside that pocket so that it would sort of neutralize that protein. Below there is a crystal, basically a material. You can think of a material that could be used to capture carbon out of the atmosphere. You can try to design that using machine learning. And then the bottom part is a catalyst reaction where, for instance, if you want to split water into hydrogen and oxygen, very important for our energy transition. That's a very inefficient process. If you can improve the materials, the catalysts on which this chemical reaction is going to take place, using machine learning methods, you'll see much better catalysts to drive these chemical reactions. Again, very important for a societal problem. So that's why I'm excited about this, because there's a huge amount of societal impact, we think, both in healthcare as well as in sustainability. Now, I've said a few things about what are the big impact areas. I've been working a little bit with the team at Microsoft in this field of weather prediction. Now, weather prediction is a particularly good example where machine learning can make an impact, because there's a lot of data. The meteorologists have stored a lot of data and made it publicly available. And so here is where machine learning methods can absolutely shine. And you can train absolutely giant sort of transformers on this particular problem with billions of parameters. And so here's sort of, over the last maybe 3-4 years, some papers that have appeared. I would argue that right now, there's been some recent papers that have, by meteorologists who've started to test these methods. And right now, they can predict, let's say, 10 days ahead, with the same accuracy as a numerical weather prediction method, which is a simulator, which tries to simulate the physical equations of motion. But now 10,000 times faster, right? So it's 10,000 times faster you can generate those solutions by basically training on the data, training a machine learning model on the data that the meteorologists have stored and provided. And this field is developing super fast, right? This is about a couple of years of progress. And I predict very soon you'll see that the meteorologists will transition from their numerical weather prediction methods to these kinds of machine learning methods, who will start to improve and improve. And probably some kind of hybrid system will evolve. I've certainly seen the meteorologists wake up over the past year to this particular new technology that is disrupting their fields, literally disrupting their field and their business. Okay, so the second part of the talk, I'll talk about what can science do for machine learning. So the first talk was about what machine learning or AI can do for the sciences. It's very exciting. But there is actually a cross-fertilization. The sciences, the insights, the deep insights from physics and chemistry can also inform better algorithms in machine learning. And in fact, this is, of course, been the case already for decades, right? I mean, if you think about, for instance, things like Hamilton Monte Carlo, which is an inference method to sample, an CMC method to sample from posterior distribution, that was first developed by physicists. You have also things like generalized leaf propagation, Kikuchi approximations, all techniques which have already been introduced in the physics community, and there's many of these examples. But I would argue that more recently, with the denoising diffusion-based generative models, this has taken a new turn. And so to say a little bit about what this technique is, I'm sure many of you already know, but so the idea is to think of a diffusion process, which is basically you start with a highly structured object, which is in this case an image of something, and you let it degrade under the sort of second law of thermodynamics, if you wish. So you turn it into noise by just weighting and adding noise to it. And that can be modeled by a drift diffusion equation, typically, it's called the Ulbeck process or something. And so you add noise as you go, which destroys the information in the image, and then the drift term is a simple linear term. Now the trick is, in order to generate images, is to see if you can reverse this process, in some sense going in the opposite direction of this second law of thermodynamics, which is to create structure out of noise, which is something we never see in the world, right? The world tends to become more chaotic, increase entropy. But by learning, we can invert this process, and it's like you play a movie backward, right? So the process at the top is a very natural one, going from a cat to noise, but the one going from noise to a cat is a very unnatural one in the physical world. But of course in a computer we can do that. And it's actually not so hard. You have to learn this particular function there in blue, which is the score function, and there's very easy ways to write an objective to try to learn that score function. It basically tells you if I'm somewhere in this process, what is the image that I predict would have generated this particular state, and so we go backwards in time. Now, that same process, as already alluded to, can also be applied to the generation of molecules. You start with a noisy blob of atoms. You don't even know the particular sort of type of atom, and from that you generate a thermodynamically stable molecule. Right? Of course, again, physics would always move in the other direction. It would disintegrate things rather than generate things. Now, why is this informed by physics? And the reason is that process is exactly the process, this diffusion process, is exactly the process that is, a gas or a liquid trying to get to equilibrium. It's the same equations. It's a particular approximation. It's called the overdamped limit, but it doesn't matter. It's basically the same equations that you use in order to relax a liquid back to equilibrium. And I will use this particular analogy now to try to come up with new models for machine learning. And in order to get there, I first need to go back to this thing called the variational autoencoder, which we developed with Dirk Kingma. So what is the philosophy of the variational autoencoder? It's also a generative model, like the one you just saw, the diffusion-based model. In fact, it turns out you can see the diffusion-based model as a variational autoencoder, as a paper by Dirk Kingma proved that, where the encoder is a fixed structure, it's just noising things up, and then the decoder is the one that tries to undo that. Now, what is a variational autoencoder? So there's two branches to this thing. The first branch is you take a point from the data manifold, which is there, this snake on the left bottom. So that's a very complicated manifold on which the data lives. And then by adding noise or by some other neural network that you can train, you try to morph that much more complicated structure in a very simple, let's say, Gaussian blob of some kind. Now that's your latent space, and every point in that latent space represents maybe an abstract concept. That if you take that and you push it through the decoder, you'll get some interesting object like a cat or something. Right, so that we call the encoder. And then there's the decoder on the other side, which generates from a prior, P of Z. And then from there, it pushes it to another neural network to generate a point that's hopefully on the manifold. Now, the manifold, it might not be precisely on the manifold of data, but at least it should be approximately on the manifold of data. Typically, things get blurred a bit, so it's a bit off the manifold. Now, the generator could be a simulator, for instance, right? It doesn't have to be a neural network. We might have a simulator there. And it's kind of interesting that there's sort of this yin and yang feature to this. which is that the encoder's task is to provide inference over the latent variables to learn the decoder. So if you want to train a generative model like that, you'll find that you'll have to first, for every data point, do inference on that particular data point. What is the latent representation of that particular input point? And in order to do that, you can use this encoder. So you can use MCMC or you can use any other technique, but the trick of the variation autoencoders is that you can do it very fast, what we call amortized. You can do it, you can train this thing over many examples. And then you can just do it very quickly by pushing that through this neural network. I guess that was the most important advance of the variation autoencoder. So you need the autoencoder to train the decoder, that's the point. Now, but you can also just be interested in the encoder if you wish, right? The encoder takes a data point and predicts a latent explanation of that data point. In fact, it could be a label that you're interested in, right? This is a cat, for instance. You can do that by pushing it through the encoder. So you could just be interested in the encoder itself as an interesting object. Of course, you don't want to just use a diffusion model because that's not very informative, but you can train this encoder. And then you can see the decoder basically as a regularizer, because you want the encoder to be the inverse of the decoder. It's trained that way, right? So so one is going backward in time, and the other one's going forward in time. You want these two things to be sort of inverses of each other. Now, if you put a simulator on the decoder side, you're putting a lot of inductive bias in that particular decoder. It tells you precisely how you want the decoder to be, what it should encode. And if you just keep that fixed, then you can sort of use the decoder to guide the encoder to do interesting inference on your inputs. And so that's what is sort of, I would say, the yin and yang. They both enforce each other, they improve each other. Right. So the second thing that we will need is something that we developed with Tucker Cohen and Maurice Weiler and Daniel Worrell and a whole bunch of people in the lab, which is this idea of infusing a neural network with symmetries. So again, this is a concept which is introduced in the physics or mathematics literature, right? This idea of symmetries and group representations that has found its way into sort of machine learning. And the idea is that if I take a neural network, I have to put in some numbers, right? I have to take, let's say, an image, and then I have to represent that image by numbers. I stick it into the neural network and I make a prediction. Now, if I would, let's say, rotate the image, I would still want a cat to be a cat. Right? So I still want the label to be invariant under either the translation or the rotation of the input of the image. Or if I do a segmentation of the image, like maybe in this figure here, you would want that if I move the cat to the right, that the segmentation also moves to the right. And you would think that's almost trivial, but the point is that actually a neural network needs to take in some numbers, and those numbers, if you rotate an image, those numbers will completely change. And the neural network doesn't understand that that's actually a rotated input image. And so you'll have to enforce it, and this is again an inductive bias, a symmetry inductive bias that you impose on your neural net. Now you can think of it as, if I have a function that goes from x to y, and I have, let's say, filterings or layer transformations phi x and phi y. Oh, sorry, that's not correct. F is the actual neural network transformation, and phi x and phi y are transformations, symmetry transformations on x and y. Then we say that it's equivariant if I first apply f, which is the filtering, and then I transform, like say rotate the image or translate the image, like for this gecko example. It should be the same as if I take the top sort of line. If I go first rotate or translate this particular gecko and then filter it. So this is a closing, a commuting diagram, as they say in mathematics, and if you force that on your representations of your neural network, you have this guaranteed equivariance property. And you can generalize this to manifolds and all sorts of other beautiful sort of mathematical structures. Now, the advantages of equivariance are data efficiency, because the neural network doesn't have to learn these symmetries anymore. They're now hard-coded in the neural network, and so it's much more efficient with data. It's also disentangling pose and presence. So it tells you something inside the neural network. There's now representations where the representation, there's a capsule which transforms in itself, which is the representation inside a capsule is represented with the pose, and the activation of the entire capsule is the presence of an object. And it also creates patterns for the next layer to latch onto, so it's also much easier to stack things this way. Now, this particular idea was used, as I said, for molecule generation by Emil Hoogboom, Victor Garcia Sartoras, and Clement Vignac in the lab. And the idea here is that you have a graph neural network. So the graph neural network, let's say, is a bunch of nodes there, like a random bunch of atoms. And now the property that I demand, if I generate something, is if I rotate this random blob of atoms and then generate a particular molecule, that should be the same as if I first generate the molecule and then rotate the actual molecule. If you force that equivariance on the generative process, you will find that the probability of generating something in any particular orientation or location is the same by construction. And that's, again, very useful because the model doesn't have to learn that anymore. Okay, so now we're going to try to generalize this idea a little bit to the idea to generalize equivariance. And so the picture you should keep in mind is that this commutative diagram. But now we're going to think of a symmetry transformation maybe as a transformation that happens in the real world. And my favorite example is, if I walk in the world and I rotate my head and I move my head, the image that hits my senses and my retina constantly gets transformed in very complicated ways. But I don't get confused. My neural network doesn't get confused. It's not like I'm seeing something completely new if I rotate my head. So somehow in my brain this is compensated for, right? That's just this idea of equivariance. But you can think of that as a prior on the world. The world doesn't change very quickly. If you look at a movie where you can sort of go from one shot to the next shot, right? As, in a movie things change very quickly. But in the real world, the world doesn't change very quickly. I mean, if I close my eyes and open my eyes, you're still there, right? There's nothing, ridiculously, big has changed. So that's a huge prior. And we have access to that prior because that's how the world works, right? And so why wouldn't we use that, right? If I was to ask myself, when we train our models or computer vision models, why don't we actually use sort of time, the huge priors that exist in the time dependencies of our world? Now we're going to say that yes, the world has lots of transformations that it undergoes, but they're all going to be somewhat slow. But let's think of those as symmetry transformations, like rotations or right? But so some kind of transformation on the world, or on something that impinges on my senses. Then I'm going to encode that data to some hidden activations. This is the stuff that lives in your brain or in your neural network, deep inside your neural network. Those are the concepts of the world. And now what I want this diagram to close, which is that if I change the world, or change my head orientation, then I want some transformation on those latent representations that are representative of that transformation in the world. Now, the hidden representations live in a very different space. Like it's a super high dimensional space. It doesn't have to be a three-dimensional space. It could be like I can have as many channels as I wish in that space. So I need to come up with some symmetry transformations on those latent representations that are representative of the stuff that happens in the real world. And again, what I'm going to try is to close this diagram. I'm going to say if I first transform the world, or if I first encode the world, and then have some transformation in my brain, and then I decode from my brain, then I want that to be the actual world after the transformation, right? So it's like you close your eyes and then you imagine what happens in the world after a bit, and you open them, and then whatever you imagine should be what you're seeing anyway. Now you can call this homomorphic representations. So we say that symmetries are input transformations that generate predictable transformations at the activation layer. So I haven't set what that transformation, the hidden representation is, so that's what we're going to do next. What are we going to put there? Right? So we have transformations in the world, we can generate those. I mean, actually, we just look at videos or something like that, but that's transformations in the world. Now, what are we going to put there in these transformations that are in the brain? And in the past, for equivariance, we used group theory, right? But what if you don't know the group representation theory for that particular transformation? I mean, you use rotations and translations, it's easy, but things get much more complicated than that. What if it's not a group in the first place, right? It's just some other transformation, maybe a semi-group or something like that. What if you don't even know what the transformation is, you just have data? Okay, and we were inspired by, we're actually collaborating now with Terry Stanowski and his group, and Lyle Miller and his group, who have been thinking about these types of transformations that are happening that are actually observed in the brain. And it turns out that they observe waves in the brain, so waves of activity. So something gets activated, and then there's some kind of wave that goes through the cortex, that sort of this activation gets moved to another place. And so this is where this analogy of this is so weird sometimes, these equations turn black, but anyway, it's good, so you don't get distracted by equations. So on my computer it works fine, but somehow on another, there's I guess, some kind of version thing. So this is where this analogy with the liquid comes in, because we're going to think of that transformation that's happening in our sort of brain as a sort of the way that a liquid would respond to a change. So to go back to the variational autoencoder analogy, so we have an encoder on the left-hand side, which takes the input and encodes it. And then there is a transformation of the world, which you can think of as a Markov process that sort of stochastically generates new states in the world. And there's another Markov process in the latent space that is also, a Markov process. You can't see it; it's blacked out. And then there is the decoding, which is again the standard thing that we do with a variation autoencoder. So it's just a variation autoencoder with a time component in it. Okay, and we had to pick. We made some choices in order to start modeling things. And the first thing we picked was this particular second order equation. If you don't want to look at the equation, you can look at the picture on the right-hand side. So there's basically, you think of this as a graph neural net. Every node is one of those steel bars, and the nodes which are in each other's neighborhood, they interact through these string systems. So you can sort of feel that if you activate one of these things, you'll just generate waves through this particular medium. Now, in more detail, there is a term there. I can't quite point because this thing isn't really well. Maybe you can see it here, but there's a term here which is a sort of a convolution of the input, both on these location and the velocities. There's a driving force coming from the actual encoding, and then there's damping terms which tries to keep the energy in check. And then there is just the second order. So this is the update on the velocity, and then there's an update on the position using the velocity. Anyway, this is just some model, and it's related to another paper by Worsh and Mishra, which is a very similar one. But in this particular model, we replaced, MLP models, with convolutions. And then what you see there on the right-hand side, these figures, are the latent representations as they evolve. And so in the first model, if you train a model, you can see something that, the latent representations do weird things, but if you take convolutions, it actually generates waves. And then we got very excited, because, you just learn it to generate these waves, and they just happen out of the learning process. Right? So how does that connect back to equivariance, if you wish? right? So you start with a sort of an image on the input side. You then encode that into a latent representation there. Then you've trained some kind of vector field, which is, you can see here, there's some kind of vector field. For instance, similar to the diffusion models, right? You also train the vector field, the drift term. So similar here. And that tells you how to move your latent representations along that vector field. And then after a while, that's your new representation, and then you regenerate the image from there, right? And in the world, we sort of take a 5 and we rotate it, right? And then, of course, you can just use this as a generative model, and you can keep rotating 5s and stuff like that. So the equivariance is, in the fact that this is a commuting diagram, right? So in other words, if I first rotate the 5 tg of x, and then I generate, it should be the same thing as first generating and then transforming. If I take the latent representation, so if I first take my latent representation and I transform and then I generate, that should be the same thing as taking the original sort of image and then transforming it. So that's the closing of that diagram, which is related to the equivariance. And you can start playing with this. You can, have different inputs, and you can look at what those latent representations look like. Some of them are more wavy than others. Some on the right-hand side got very complicated because there wasn't enough capacity, and it was trying to get too much out of too little latent variables, and so we sort of a bit over-regularized. But I find very interesting thing that happened when we did this. So if you look in the brain, in fact, you'll find, if you look at all the neurons in the visual cortex, they're all tuned to particular directions. So if you look at edges, then you're tuned to particular directions of these edges. And it organizes in a way that you can sort of see on the left-hand side here. Or there is actually the measurements that people have made. So they're clustering. So this orientation sensitivity is clustering. And it has this funny topological defect features, is where all of these sort of orientations come together in a single point. So it becomes a topological defect called a pinwheel. Now, if we take our model and we train it, it generates waves, and then if you wait and you then look at the latent representations and see how they organize themselves, you get precisely this kind of orientation tuning. And precisely why that happens, I don't know, but certainly it is intriguing that this just imposing something simple like a wave equation on your latent space does this for you. Now, the final thing I want to talk about is that this particular idea can be used to build disentangled representations of the world. And so to take you through this, the first thing I want to say, there's a beautiful paper called the Computational Fluid Mechanics Solution to the Monge-Kantorovich mass transfer problem, that's basically stating that you can think of a fluid basically as solving a optimal transport problem. So if a fluid moves from one point to another point, it evolves, it's trying to sort of, in some sense, solve an optimal transfer problem and sort of finding the shortest distance in terms of probability density space. Now, again, very similar to what I described, so we have some input space here. So we have some images, and we have some transformations on these images, right? So here's a tube, and I can turn it green, which is one type of transformation. I can scale it to make it bigger, which is another path through world space. And there's another path where I rotate it. Right? So here you can see the scaling happening, you can see the change of color happening, and you can see the rotation happening. So every one of these sort of transformations is some path in the space of the world. Then we have an encoder which maps these points to some latent representations. So the points, the red dots here, are the actual latent representations as in any variational autoencoder. But now we have this other thing, we have these transformations that we also observe, let's say, in the world. And we don't have to actually know the labels for them, we just have to see these transformations, and it will figure out itself, ways in which it can sort of model that. And they follow this vector field. So if you take this particular, you can think of this as solving a wave equation if you wish. So you take this point, and then these latent representations, they move according to this vector field to this other thing, this rotated or scaled version of this particular image. And you can model that by a vector field. It's actually the gradient of a scalar field. And that's basically the continuity equation. You can make this in phase space, and you can make it oscillatory by having positions in momenta. And just by putting that particular continuity equation as a constraint on how the latent representations should change, you'll get basically you'll learn these representations, and I'll show you a few examples. You know that at every point it's not just that you have the actual latent representation, you also have a bunch of directions attached to that point which tell you if I go in this direction, the image will scale. If I go in this direction, the image will rotate. Right? And so the representation is now disentangled in the sense that it represents the point, but it also understands how to transform this particular image into new images. And here you can see we just trained it on, we just gave it a bunch of transformations, and then you can ask it things like, okay, let's start with a rotation and then change the color. I've never seen that combination before, right? And then this is what it generates. It first rotates and then it changes the color. Or if I first rotate and then I scale, right? So it understands these transformations now very well and knows how to represent them in space. Or here's another data set where you can just do roll hue and then object hue changes and stuff like that. But even better, you can now start to combine these transformations, right? You can, for instance, change roll hue and scale at the same time. It's never seen that. It's only seen roll hue change or scale changes, but it understands that it can still linearly combine these transformations and still, give you reasonable generations. Okay, so I'll slowly conclude. I started this talk by saying that there's huge opportunity at the intersection between AI and science, and I've given a number of examples of that. And I would say particularly, let's say, in materials science and biology, molecular biology, there seems to be huge opportunities. These fields themselves, of course, are very mature and advanced, but more recently what has changed is that the computational science, we have huge computers and we can simulate very well for these equations. We now have machine learning and deep learning, and then hopefully in the future we'll also have quantum computing, and all of these modeling sciences, modeling technologies will really help model these fields very well. And maybe more importantly, there's going to be a huge pull on the application side. In healthcare, designing new drugs for new diseases, maybe for cancer, maybe new vaccines, maybe new antibiotics for resistant bacteria strains. In the energy transition, building new catalysts for splitting water into hydrogen and oxygen, or perhaps new fertilizers, design of new fertilizers. And in sustainability, new materials, let's say, to capture carbon out of the air, and new plastics that are biodegradable, etc. And what I'm excited about this is that, in some sense, we've always named the age in which we live by the materials that we use, right? We started in sort of Bronze Age, Iron Age, etc., etc. We've progressed all the way to the plastic age, and who knows where we're heading with this. But what I want to say is that we might, at some point, be in a position to basically design a material on demand. I can just say, I want a material with these particular properties. Generate candidates for me with molecules that have those particular properties and that are synthesizable and they're not toxic. And then this system, this search engine, if you wish, could produce those molecules for you in a computer, which you can then synthesize. That might be a huge revolution, right? Because we can then absolutely start to think about very strange materials with very strange properties that we may want to make. Right, so there's a rich synergy between AI and natural sciences, I've argued. I've talked about generative AI and generalized equivariance that turns into some kind of temporal VAE with a liquid latent state. So trying to use an analogy from physics, basically the continuity equation, to try to model how latent states evolve. It needs to leave new views on how to build equivariances or symmetries or generalized symmetries into models in terms of disentanglement. What does it mean to disentangle a representation? Maybe it just means that you know how things transform. You apply some transformations to it. Very interesting, intersections with brain waves and topographic map formation. So maybe our brain has sort of come to a similar solution in the end. And it's also posed lots of constraints on how these neural networks process information. It would be very exciting to see if that process is modeled by this. And then I'm most excited about these applications, both in climate science and health. There's new materials and catalysts, new drugs and vaccines, and also better models to predict the weather and the climate. And I'll end there. Thank you very much.
Thank you so much for the fascinating talk. All this interdisciplinary cross-fertilization, as you called it, is really intriguing. So we have a bit of time for a few questions. So there are two standing mics here, on the left and the right. If you want to ask a question, please stand up and go to the mic. And while people think about their questions, I'll make an announcement for all the presenters that have to present today, both in the plenary session, after this session and after the coffee break. And for this afternoon, please, we need your presentations. If you go here on the left, on backstage, our volunteers will help you, load the presentations on the machines. So please come here after this session. All right. So we have a first question here.
Yes, thanks. Very interesting talk. This is Jian Wang from the environment part of County. So you said a very interesting approach using temporal VAE and convolutional to variance to model and learn how like the waves and the number rotate and color changing. But in the real world, things are more complex than that. For example, the shape of from liquid to solid, from snow to rain, those are more complex transformations. What do you think of the methods might be able to learn those kind of transformations? Thank you.
Yeah, this is a great point. So we've only applied this to some of the standard data sets that are out there that people compare these models with each other. But I agree that it should be tested on real image sequences. My hope is that it will automatically find consistent sets of transformations that it then will encode as different directions in the space. And then if you sort of activate, let's say, one of these, you'll see some kind of, stereotypical transformation that will just maybe change, the light of the day, because that might be happening a lot, or the contrast, because a car driving into a tunnel or something. These kinds of typical transformations that are happening on these images, and my hope is that it will sort of unsupervised discover these things. But I agree with you; it's a very interesting topic to see if we can actually do that, and what will come out. That should be the next step.
I just wanted to ask if you have any intuition on why the diffusion-like process of gradual denoising or learning the vector field, as you put it, seems to work better than one-shot generative approaches.
Okay, that's for diffusion-based models in some sense, right?
Yes.
Yes. Okay, so the idea is that it's easier to predict a small change rather than a huge change in some sense. Because, going from noise to, yeah. Also, I would say that you have a noising process where you have all of these little steps, and it's kind of, the changes in these small little steps are easy to sort of invert. Right? That's a much easier, because a small change from one layer to the next layer. Now, if you make a huge change, it's a much harder modeling problem because a lot has changed, right? And so I think it's this idea that small changes are easy to model and big changes are much harder to model. That sort of underlies this particular issue. But I don't see a fundamental way where you can do it in one shot. People have tried it. Of course, it's very expensive to generate if you have to go through 1,000 iterations. And so people have really tried to reduce the number of steps in this diffusion process. And there are interesting ways in which you can do that. And that's very helpful, but yeah, so I don't know the full answer to that. That's also a very interesting thing to look into, but certainly it's very important because this generation stuff is very expensive on a computer. If you can reduce the number of steps, it will actually be very helpful.
Thank you for the talk. It was very interesting and somewhat inspiring. I was wondering for your generalized equivariance setup, it would seem that enforcing these properties on the latent space would act as a regularizer, but at least similar things did not happen for the equivariant or group equivariant neural networks. So I was wondering, do these enforcements have regularizing effects, or are they actually beneficial to better performances?
Okay, so the answer is they are definitely regularizers. I also think that equivariance with known groups is an even stronger regularizer because it ties together the parameters of the layer, so that's a very strong regularizer. Basically, you're removing a lot of degrees of freedom, if you wish. Now, the point is that if in machine learning more generally, if you put in the right inductive biases, that is the right regularizations, you should do better than if you don't put anything at all, right? And so the whole game of machine learning, in my opinion, is finding exactly the right inductive biases so that you can learn with less data in some sense. You don't have to learn everything from data. You can just learn with fewer data points because you've put in the right information or priors already in your model. And so that's the search for better models in some sense. Now, deep learning has sort of thrown a bit of a wrench in that reasoning in the sense that very, very large over-parameterized models also happen to generalize very well. And that's kind of interesting in its own right, but not putting any, but you need a huge amount of data to train these models, so that's the downside. But yeah, so that's, I guess, my answer is that I want to find the right inductive biases. It's slightly relaxed relative to full equivariance, but it's more than not imposing anything at all.
So we have time for one more question, because then we have to go for a coffee break, but I guess you can catch our speaker at the coffee break.
Thanks for the talk. I think it's a really amazing thing that you presented. Maybe a bit too early for this question because I realize, yes, it's still some work in progress. But one thing that I've thought about now seeing this is the dimensionality of what you're looking at. Because if you have, for example, 4 or 5 independent symmetries, then if you want to walk through this latent space, then you also need to have these 4 or 5 independent directions that you can go there, right? So with the normal neural network implementations, we have convolutions in 2 dimensions and 3 dimensions, but wouldn't you need then also to have these higher dimensional kind of structures in how these things connect?
Yeah, you can make your latent space as high dimensional as you want, and it doesn't have to be a basis, right? You could have one direction, you can have another direction, you can have combinations of these directions. But I agree that if you wanna host many transformations, you would like to have a higher dimensional space. It's easier to find more directions to model this in. It's probably going to be beneficial. Yeah, but it doesn't have to be that if you have only a two-dimensional space, that you can only model two transformations because it's the whole path really that counts, right? It's just, I mean, yeah. I think but the short answer is higher dimensions will be helpful here, but I think you can still already do quite a lot in low dimension. In fact, the models that we show here are quite low dimensional, it turns out, and you can already store a lot of these transformations in that particular low dimensional space.
All right, thanks again for the talk, and enjoy your coffee. We'll get to the presenters and here on the right for the good presentations. Thank you.